Hello, my name is Pham. I'm a PhD student from Carnegie Mellon University, working with Dee from Peking University and Feras and Yang from Carnegie Mellon. Today we present Programmable MCMC with soundly composed guide programs. So to set the stage, let me first introduce probabilistic programming. The user first writes a probabilistic model, which is a joint distribution of two random variables, theta and y, as a program. And this model program may contain conditional statements and loops. Here we have two random variables, theta and y. Theta is a latent variable, which we want to infer, and y is an observed variable for which observed data will become available. Next, the user collects observed data, d, and use it to compute the posterior distribution, which is given by Bayes' rule on the slide. The denominator of the right-hand side involves an integral of the space of theta. Because this space is usually high-dimensional, computing this integral is intractable. So instead, in practice, we run a sampling-based inference algorithm, such as Markov chain Monte Carlo, or MCMC for short. It works by running a Markov chain that is carefully designed to converge to the target distribution. We start with some state, theta 0, on the slide, and we propose a new state, theta 1 star, by drawing a sample from a proposal distribution Q. We then probabilistically jump to this state with some probability, otherwise we stay in the old state. And we repeat this step many times. And the collection of samples drawn from this Markov chain serves as an approximation of the target distribution. As a running example throughout this presentation, I will next introduce Bayesian polynomial regression. The model program works as follows. It first probabilistically generates the polynomial degree d by sampling it from a categorical distribution with 3 buckets. So the degree in this example is either 0, 1, or 2. Next, the model probabilistically generates a constant coefficient, C0, for the polynomial. And depending on the value of the degree, it additionally generates linear and quadratic coefficients, C0, C1 and C2, if necessary. So the set of random variables generated in this model depends on which execution path we take in the model. And lastly, the model generates observed variable y around the polynomial function that we just generated by adding some random noise. So if we run this probabilistic model, then we obtain these prior polynomials with various degrees ranging between 0 and 2. And the goal of Bayesian inference in this example is to answer this question. Given the observed data for y, what are the likely degree and coefficients of polynomials that generate the observed data? So, for example, given these red points on the slide, our goal is to infer or approximate a posterior distribution of polynomials like these black curves on the slide that likely have generated the red points. Traditional probabilistic programming languages use a generic inference algorithm that is applicable to all Bayesian inference problems, but it may perform poorly by failing to converge to the target distribution quickly enough. This is the result of running a generic inference algorithm in our running example of Bayesian polynomial regression. For this plot, we draw 50 posterior samples of polynomials. And as you can see, many of them overlap. So there's little variance within these 50 posterior samples. And it means that the generic inference algorithm does not effectively explore the space of posterior samples. To this end, modern PPLs such as Wang and Pyro support programmable inference, where the inference algorithm is customized by a user-written program called a guide program. Specifically for MCMC, this guide program customizes a proposal distribution used in a Markov chain. In this work, we study a variant of MCMC called multiple block metropolis hastings, or BMH for short, which samples random variables block by block. So to give you an example, let's say in Bayesian polynomial regression, the user splits the set of random variables into 4 blocks, each of which contains exactly a single random variable, namely d, which is a polynomial degree, and the 3 coefficients, C0 up to C2. Additionally, the user specifies the proposal distributions for each block. To customize the inference algorithm this way, the user writes 4 guide programs, one for each block. In BMH, we run these guide programs one by one, where in each guide or each block, we sample those random variables in the block while keeping other random variables unchanged. So back to our example, let's focus on the first guide, GD, for the polynomial degree D. It first samples the random variable D, and for all the other existing random variables, it simply reuses old values. And after running this guide, we obtain the trace sigma 1 star, which stores all the values of the random variables. And then we perform the so-called MH update, where we probabilistically select the newly proposed state. Otherwise, we stay in the old one. And then we pass on this trace to the next guide, and then repeat the same step for the remaining guides. And this is a result of running BMH on our example. As you can see, this time we now have more variance within the 50 posterior samples generated by BMH as compared to the generic inference algorithm from the previous slide. So by customizing the inference algorithm, specifically by splitting the latent variables into blocks and sampling them block by block, we obtain more accurate posterior samples, also more quickly. In order for BMH to converge to the target distribution, it should satisfy the sufficient soundness condition that the model and guide must have the same support. For instance, in a guide program for the quadratic coefficient C2 in our running example, let's say we replace a normal distribution where the support contains all reals with a gamma distribution where the support now only contains non-negative reals. Then it results in unsound BMH because now the guide is unable to sample negative values for the quadratic coefficient C2. And the result of this unsound BMH is on the slide, where clearly the posterior distribution of polynomials does not fit the red points, namely the observed data. So in this work, our contribution is the following. We developed a type-based framework for statically verifying that the model and guide have the same support for BMH, which is a key soundness condition. And this is checking this condition statically is challenging because the set of random variables depends on which execution path we take in the model and guide programs. So now that we have motivated the static analysis of BMH to check its soundness, next I will describe our 3 contributions, namely formulation of BMH, polynomial time decidability of structural equality, and coverage checking. And at the end, I will briefly discuss our implementation and evaluation. So for our first contribution, we formulated BMH as a sequential composition of guide programs, as illustrated on the slide. So for our example of Bayesian polynomial regression, because we have 4 blocks, we also have 4 guide programs. In the bottom row, so GD up to G of C of 2, and each guide communicates with the model program M. So this is the formulation we use to model BMH. And the communication between M and G is done by message passing. Specifically, this guide, so let's focus on the first guide, GD. So it takes as input the old trace, sigma 0, which stores all the old samples of all random variables. GD then draws a sample for the random variable D and sends this sample to the model program M. And when we reach a conditional statement in the program, it is the model's responsibility to decide which branch to take, and this branch selection is sent back to the guide. And this communication continues between the model and guide until they terminate. And once we obtain a trace after running the guide G, then we perform the image update where we probabilistically select the next trace to be passed on to the next guide. And then we repeat the same step for the remaining guides. And this communication protocol between the guide and protocol, the communication protocol between the guide and model is described by this guide type on the slide. So here N3, which denotes the distribution type of the random variable D, captures the support of the distribution from which we draw a sample for this random variable. Because the polynomial degree was generated from a categorical distribution with 3 buckets, it's the corresponding distribution type is N3, where the subscript 3 means that we have 3 buckets in the categorical distribution. And the ampersand in the guide type means that we have a conditional statement. And if we pick the first branch, then the guide terminates because there's nothing else to sample for. So this termination is denoted by the guide type 1. Otherwise, in the second branch, the model and guide continue their communication to additionally sample for the linear and quadratic coefficients. So in this formulation of BMH, a key soundness ingredient is that the model and guide must have an equal guide type. Because otherwise, the communication between the model and guide will fail. And guide types in general can be context-free types, which are types indexed by type parameters. An example of a context-free type is on the slide, where T is a type name and X is a type variable. So the intuition of the guide type Tx is that we first run a protocol T, followed by some continuation captured by the variable X. And if you look at the definition on the right-hand side, it says that we first draw a sample with the distribution type R, followed by a choice between 2 branches. So that's denoted by the ampersand. And if we pick the first branch, then we simply proceed with the continuation protocol X. Otherwise, in the second branch, we run T of X. And the intuition is that we run the protocol T twice, sequentially, followed by X. And guide types may have infinite state spaces because, for example, on the slide, as we walk through the type and unfold its definition, we get Tx and 2 T's of X and 3 T's followed by X and so on. So to check the structural type equality of guide types, we cannot simply exhaustively explore the state spaces because they can be infinite. So our second contribution in this work is to prove that structural guide type equality is decidable in polynomial time. To show it, we first translate guide types to context-free processes, which are basically context-free grammars viewed as processes. Next, we require that the norms, namely the number of steps to reach termination from any state in the guide type, to be finite. And this is a sensible requirement in the context of probabilistic programming because we expect probabilistic programs to eventually terminate and return finitely many samples instead of running forever as in networks. And lastly, we appeal to the theorem proved by Hirschfeld and his colleagues in 1994 that the bisimilarity of 2 context-free processes with finite norms is decidable in polynomial time. And thanks to our translation from guide types to context-free processes, it also means that the structural guide type equality is also decidable in polynomial time. So next, I will talk about coverage checking. So given a sequential composition of guide programs, every random variable must be covered. That is, it must be sampled freshly by some guide program in the sequential composition, regardless of what execution path we take. Because otherwise, if some random variable is never sampled by any guide in the sequential composition, then the model and guide will have different supports for that particular random variable. And a more formal program statement of checking coverage of random variable is the following. Let's say we are given an arbitrary initial trace sigma 0 and an arbitrary final trace sigma b. So pictorially, we are given a sequential composition of guides, and we fix an arbitrary initial and final traces. Then the question is, do there exist intermediate traces, sigma 1 to sigma b1, sigma b minus 1, such that for each I, the guide gi can generate the desired trace, sigma I, using the previous trace, sigma I minus 1. And in the interest of time, I will only give a high-level idea of the coverage checking algorithm. But the basic idea is that we first annotate guide types with coverage annotations to track which random variables have been sampled, using subscripts U and C to indicate whether a given random variable is covered or uncovered. And then, given a sequential composition of guides, we walk through them one by one to update the coverage annotations whenever random variables are freshly sampled in the current guide. And then at the end, we check the coverage annotations of all random variables to see whether they are all covered. And if that is the case, it means that all random variables are freshly sampled at some point during the sequential composition, which means that the BMH is sound. So lastly, let me briefly talk about our implementation evaluation. So we implemented an algorithm for checking structural type equality and embedded it into type inference. For the benchmarks, so this is the table which is available on the paper with more details. But for the benchmarks, we reuse the benchmark programs from the previous work by Wang and also his colleagues from PLDI 2021. And we split each benchmark into multiple blocks. So we basically use BMH for each benchmark. And then our evaluation shows that some BMH benchmarks require structural guide type equality instead of simple, naive, syntactic type equality to be able to infer types. And we also implemented an algorithm for coverage checking, and our evaluation shows that our algorithm is effective for those benchmarks where the state spaces of guide types is finite. But for those benchmarks where the guide types may have, or the guide types have infinite state spaces, then our coverage checking algorithm can return false negative because the algorithm is sound but incomplete. And for more details, yeah, please look at the paper. So in conclusion, we made 3 contributions in this work. First, we formulated BMH, which samples random variables block by block in the guide-based framework of programmable inference as a sequential composition of guide programs. We additionally proved polynomial time decidability of structural type equality for guide types, which in general can be context-free and hence have infinite spaces. And lastly, we developed an algorithm for checking coverage of random variables to statically verify that each random variable has been freshly sampled by some guide in the sequential composition, which is a key soundness condition for BMH. Thank you.
So questions. We have time for a couple of questions. Okay, I have a question.
Sure.
So if a program fails your verification, what kind of feedback you give to your program to fix the program?
So we didn't really investigate the kind of error messages that we can return to the user, but okay. So first of all, for equality checking of types, so let's say the guide and model have unequal types, then we can return some intermediate sort of states of the algorithm that we use to check type equality, and those intermediate states may be useful to the user. But back to your question, we don't really consider sort of we don't aim to return useful error messages. I think that would be the future work.
Yeah, I would love to see it. Thank you very much.
Yeah, thank you.
Okay, let's thank the speaker again.